In this video, I'll do some examples that will help with your Chapter 12 Thermodynamics assignment. So the first question talks about a coffee pot where you're given the power of the coffee pot, 750 watts, and you want to know how long it's going to take to bring the water in the pot to a boil. So let's write down what we've got here. We're told power, symbol for that is P, is 750 watts. Now we're told the volume of water, 0.75 liters, but the density of water is 1 kilogram per liter. So 1 kilogram per liter is the density. And so the mass of water that we have here would be 0.75 kilograms because the heat equations uses mass, so you need kilograms. Okay, and we have the pot that has to warm up as well. And whenever water is in any kind of metal container, you can always assume that the pot and the water are at exactly the same temperature pretty rapidly. Like you would not want to hold on to a metal cup and have me pour boiling water into it because it would just rapidly burn your hands. So the mass of the cup is 280 grams. Now, we can either use grams or kilograms. We don't have to use either one exclusively, but we've got to make them the same. So how about we let this be kilograms, 0.28 kilograms. Okay, and we're not worrying about boiling, so we have no phase change here. We're just worried about heating this up. And so we know that the amount of heat to change the temperature of an object is mc delta T. Okay, and we've got the cup and we've got the water. So the total amount of heat here, total would be mc delta T for the cup plus mc delta T for the water. Now the changes in temperature, the initial temperature of the cup and the water is 11 degrees Celsius, and the final temperature would be 100 because it's just coming to a boil. So you would have to know the boiling point of water. I think everybody does know that. It's 100 degrees Celsius. Freezing point of water is 0 degrees Celsius. So the change in temperature here is 100 minus 11, and so it's 89 degrees Celsius. Now you'd also have to know the specific heat capacity of the cup and the specific heat capacity of the water, which you would have to be given. And turns out specific heat capacity for water. Now beware of this number. You're going to see all kinds of different things depending on where the problem has come from. So you may see 4186 joules per kilogram degrees Celsius, which is what the solution that I'm going to use will use. But beware, you may also see 4200 joules per kilogram degrees Celsius for water. You may see 4190. And so it just all depends on the problem. And you may just be frustrated because you're going to use 4186, but the solution may be used 4200. So just beware of that. Okay, and then for aluminum as well, depending on your source, sometimes you see 900, sometimes you see 920. This particular problem is using 900. So that is also another source of frustration. Hopefully these numbers will be given in the problem, so then you know which one to use. Okay, so we can calculate how much heat this is. We would just have to multiply all these numbers together. The mass of the cup times specific heat capacity of the cup. Now the change in temperature for both is the same. It's 89 degrees Celsius. And then the mass of the water, 0.75 kilograms, specific heat capacity of the water, and change in temperature of the water. And if you put all that in, I don't know what you get, but that's the total heat. Okay, let's just go straight ahead to so you guys can calculate that, put that, you're going to get some number of joules. Now the power, how is power related to the heat? Well, power is the rate of use of heat or the rate of generation of heat, depending on the application. So this power is equal to heat divided by time. So this would be Q over T, which means if you want the time, you take Q and divide by the power. So it would be, you would take the Q that's just calculated in the line above And then you would divide that by 750 watts. Okay, so you can check out this answer. It should be, this will give you seconds, 4.02 times 10 to the 2 seconds, or 6.7 minutes. Okay, so that's example number 1. Example number 2, you can pop back up to the top to read it. I'll just read it to you here. So we're trying to find now the equilibrium temperature when a 265 gram block of copper at a given initial temperature is put in a cup that has some cold water in it, 12 degrees. So for these kinds of questions, I like to look at each, like draw a little picture. So you've got this copper, and it's at 245 degrees Celsius. It's hot. It's been in some oven or something. And now you're going to put it into this cup where there's water. And if they give you the mass of the cup, then you have to worry about the heat that the cup will absorb. If you're not given the mass of the cup, then you don't have to worry about it. Okay, and these are at 12 degrees Celsius. Okay, so these are cold. And then after everything is mixed together, you've got this pot, you've got this block in there, you've got the water, and it's all at some final temperature, T final. And this is the equilibrium temperature. And you assume this takes place in a calorimeter, so you're not losing a lot of heat while that all comes to equilibrium. And this is the question. We're trying to find this unknown temperature. Okay, so I don't like to use negative numbers when I'm doing my delta T. So what I always do is heat lost equals heat gained. Okay, and then I like to make a table. So we've got 3 things going. We've got the copper, we've got the water, and we've got the cup. So let's make a table here. And in the table, we'll have the copper, the water, and the cup. So those are the columns. The rows are going to be the mass, the specific heat capacity, and the change in temperature. And then we're going to add these quantities vertically to get the heat for each of these objects in the problem. So let's fill this in as best we can. Now, if everything's given in grams, just leave it in grams. All the grams will cancel across the equation. So we've got mass of the copper, 265 grams. Mass of the water, 825 grams. Mass of the cup, 145 grams. Okay, specific heat capacities of all of these, you would have to be told. So for copper, it's 390. Now, as long as the units across the row are the same, it doesn't matter what they are, because they will all cancel. So this is joule per kilogram degree Celsius. I'm not going to write that out, though. The water, 4186, specific heat capacity, and the aluminum cup, 900. Okay, now the tricky thing is the delta T, the changes in temperature. First of all, I like to go to my columns and decide which one is losing heat and which one's gaining heat. The copper starts out hot and then cools off. So this is losing heat. So this is a loser. The water and the cup, whatever they do, they always do together. That's a gainer, and this is a gainer. So I know that in my equation, heat lost equals heat gained, that it's going to be Q for the copper is going to be Q for the water plus Q for the cup. And everything, I want positive numbers everywhere here. Okay, I don't want to use that the change in heat is 0 and then I've got negatives all over the place and it just causes chaos. Now, if we're going to have positive numbers everywhere, it means every delta T is hot minus cold, always. So delta T is hot minus cold. Doesn't matter whether it's a gainer or a loser. If you just use hot minus cold, you will get the correct things in this equation. Okay, so let's see what's happening. Up here, this final temperature obviously is going to be somewhere between 12 and 245. So the copper hot is, so this is T hot for the copper. And TF would be its cold. So it's going to 245 minus TF would be the delta T here. So this is 245 degrees minus whatever that final temperature is. We don't know, but it's definitely less than 245. Now, because the water and the cup are gaining heat, this final temperature is warmer than 12. And so its delta T is TF minus 12. So notice how those are flipped around because I want a positive number. And whatever the cup does, the water does. They're all the same. Okay. Now TF is our unknown, and this is why this is a little bit of a messy question here. So if I go down here, I'm going to get mass of copper, Cu, times C of copper times 245 minus TF. For water, mass, water, C, water, but this is TF minus 12. Plus mass, aluminum, C, aluminum, and TF minus 12. Now, before I put numbers in, because it gets kind of messy when you put numbers in, try to solve this for TF, and you'll see the symmetry and how these just fall out nicely, and TF becomes this positive number. So you have to multiply through the brackets everywhere here. So the mass of copper, C, copper times 2, what was it, 254 or 245? Whoops, I got that wrong. It's 245. Careful here. 245. 245 minus M copper, C copper, TF. M water, C water, TF minus M water, C water 12 plus MaCA plus, sorry, minus MaCA12. Now let's get all the TF terms on one side and all the other terms on the other side. And notice what happens. Everything becomes positive. I'm going to bring this way, it becomes positive. These two guys, which are negative, when they go that way, they become positive as well. And look how the symmetry falls out here. That I'm going to get all the TF term, write them first. So M water, C water, TF plus M aluminum, C aluminum, TF. This is the right-hand side of the equation. Now it's plus copper, copper, TF equals, now get all the other ones to the other side. And they're all positive as well. So we have the M copper, C copper, initial temperature of the copper is 245. Plus M water, C water, initial temperature of the water is 12. And then M aluminum, C aluminum, initial temperature is 12. And so look at the symmetry there. If I factor out this TF, I get the product of all the MCs in the problem. Copper, C, copper. And on the right-hand side, I have the product of all the MCs times their initial temperatures. And they're all positive. And so you can see what the final temperature is. Product of all the MCs times in their initial temperatures. And you could just add as many objects to this as you want. You could add thermometers and, I don't know, extra things in the water or whatever. And then on the bottom, you just have the product of the M's and the C's. Now you cannot cancel anything here. The M's and C's don't cancel. You have to multiply all this out. Okay, but you can see everything's positive. You can see the units. The MC units at the top cancel the MC units at the bottom, and you're left with these temperatures. These are temperatures, degrees Celsius, degrees Celsius, degrees Celsius. Your answer is going to be in degrees Celsius. And the answer is, you can check out, put all those numbers in, is 18.5 degrees Celsius. Okay, so that's how you do these questions where you need to find the final temperature. You can almost just jump straight to this TF to get the answer. Okay, and then the last question I want to do here is not, TF isn't unknown, but the specific heat capacity is unknown because you have this in your lab. So question number 3, we're trying to find the specific heat capacity of an unknown metal. And that's what you're going to do in your lab as well. Now the setup is exactly the same as the one above. you do the columns, you put all your objects in, you put the losers and the gainers. Now, it's a hot sample of this unknown substance. And now we have the cup, we have the water, and we have a thermometer. But now they're going to tell us the final temperature, so that makes it a little bit easier. So you still want to do your, so this is the unknown substance. Make your table. And then you've got the water, the cup, and you've got a thermometer in the cup. So that's going to take up some heat too. That's why you have to put it in there. Okay, so these are our columns. And then we want to put the MC delta T in for each of those. So you keep it straight, and then you can just at the end put the numbers in. Okay, so we're told all these things. This unknown substance, 215 grams. The cup, 105 grams. The water, 185 grams. The thermometer, only 17 grams, but you still have to worry about it. And they tell you it's glass. Okay, and then you need the specific heat capacity. So the unknown, this is the unknown. Unknown. You can't have everything in this table. You have to know unknown something. 4186 for the water. It's an aluminum cup, 900. It's a glass thermometer, so you have to be told the specific heat capacity of glass. It's 840. Okay, now the delta T's. Hot minus cold. And so what are the two temperatures? We're going to have three temperatures. So the hot metal starts out at 330. And then it goes into this thing with the thermometer in it. And the temperature of this initially is 10.5. And then when everything comes to equilibrium, you've got this inside with the thermometer and the water. The final temperature, TF, they tell you, is 35 degrees Celsius. So hot minus cold. For the metal, goes from 330 minus 35. So this would be 330 minus 35. So that'd be what, 295? Remember, hot minus cold. Okay, and then for the everything else, it's 35 minus 10.5 because it's hot minus cold. So this would be 35 minus 10.5. And this would also be 35 minus 10.5. And this would be 35 minus 10.5. All positive numbers. All, and what is that? 35 minus 10 would be 25, 24 and a half. So their delta T's are all the same and always positive. Okay, then you put gainers and losers because you're going to put them on opposite sides of the equations. The unknown substance is the loser, so it loses heat. These three guys are all gainers. Gainer, gainer, gainer. So you know, now you just have to put all those numbers together. That MC delta T for the unknown substance equals the MC delta T cup plus MC delta T water plus MC delta T thermometer. Now the unknown is this one. So that C unknown would equal to all this stuff on the right. I don't really want to write it all out again. Well, I'll do it. And you've got this. You just go down your column and pop these numbers in. You don't have to put the units in anymore because you've got all the units sorted out in your table. MC delta T thermometer. And then you divide by M of the substance times delta T of the substance. And that will give you your unknown specific heat capacity. And it turns out, and make sure you don't get a crazy number like, you know, way bigger than water, because not many things have specific heat capacities bigger than water. or like you can never get a negative number. And it's not usually a tiny number either. So it turns out to be just a nice normal number, 341 joules per kilogram degree Celsius. Okay, so those are the examples that should help you with your thermodynamics assignment.